Sriman, Mike. No, that one, this one.
If you want that,
so what basically coalition games is like when players cooperate and they want reward, and how the rewards are shared between them. That is Shapley value basically. But what coalition games is, for example, take one party is there in a state, they want some X number of seats, and another party you take, they want some Y number of seats, but one more party is there, they want some Z number of seats, but that X plus Y is more than that, X plus Z is more than that Y. So X and Z will be cooperating and they will be like sharing the reward. So how equally then they will win, then they will form the government. Then based how the seats should be distributed to each party X and party Z, that is Shapley values. How they are divided, that is Shapley values. By that we will be knowing. And so like, these are the situations like firms form alliance, parties form government, cities share infrastructures like the limits. Even if you take some sports or something, for example, take Australian team, there will be 3 players like Ponting, Bretley and take Gilchrist. If you take 3 people, for example, they want some game, they want some money for some particular game. So if you need to calculate, they were cooperated, they are in same team, so they won the match and they are receiving some reward. So how the money should be distributed, we need to see that. So if you remove one person, for example, Ponting, if you remove that one and you take only Gilchrist and this another Bretley, you will be getting some amount would be there. And if you remove Gilchrist and you will be having these 2 people, that amount will be there. Like all possible cases you will be listing first, and based on that you will be giving Shapley value. There will be some formula to calculate that. First, you need to calculate all possible. For example, 3 means 3 factorial. So 3 factorial 9, 6. No, 6 combinations should be there. So like that we will be checking. So this is the definition of the coalition game. Coalition game with the transferable utility pairs where like V 2 power n to R. So this is the characteristic function for this one, and this is the value. This is like value of each coalition pair. Like each coalition, for example, pair AB, pair A, they will be having some value for that's what. So if you take here, like each will be having some value. Like AB combined will be having some value. Some value will be having some 10. This one from AC, if you combine, they will be having some value 9. So that is that we represent that only. Yeah. So for null set it is 0. That is obvious thing. Then there are some theorems like additivity. This one additivity and additivity symmetry. There are some theorems like what this additivity does is like it can be added. See, for example, V of 1 plus V2 of S can be like this is like kind of this kind of distributive you can say like this can be V1 of S can be taken separately, V2 of S can be taken separately, like independent kind of thing it is. And if you see symmetry, even symmetry you can see here. If you do union, like if you do union with that. For example, there is one I is there and one J is there, so that it is union compatible. This one, that is symmetry actually. Then efficiency is like sum of each each pair of values should be equal to the total value of all combined. And this is like dummy player. Dummy player is just it doesn't add any value to the game or something like that. That is dummy player. For example, some substitute player you can take who didn't use only in a game. Okay, so this was like this basically based on fair division only. Shapley value is basically based on fair division only. How for example, see if three person are sharing some food money, total food money. A person X can eat some amount of food, B can eat some amount of food, and they should be paying for their food only. Like total they will be having some money, but it's not that like they do, for assume a situation where they don't know what they ate only, but they know who ate how much, like who ate more that they know. So Shapley value is based on like basically it just gives which person eats what, like that, like basically divides money based on that, those things and all. So this is like what this term means. What this term mean is like you are taking from the set S and you are including the particular player I, and this one like Yeah, and you are removing that. Yeah. So basically, each player if you add that player, what is the effect? What is the effect you are saying? Like I told before, if the three players are the Ponting, Gilchrist, and Bretley. If you take all of them, if you remove Ponting, what is the value of reward you are getting? If you remove Bretley, what is the reward you are getting? And like without them, kind of removing them and checking and giving them, assigning them the particular value. That problems we'll see in future. Like we'll see next. Yeah, this is like one small example it is given. So there are two partners are there. V1 alone will be having some value 1, V2 alone will be having some value 2, and both of them combine total marginal cost is around 4. So using Shapley value, we need to find this one who contributed what, like that it is. And one more thing, like order, order also matters here, because if first A does first and B does first, that order also matters here actually. So there is another example. This is the formula for Shapley value. So what is this one is? See, actually for each player we need to calculate. So for this n comma v is like including each terms kind of thing. So v for a v, and this is like n factorial is like n is like which and all doesn't have I, like which terms doesn't have I. So that is n. So no, sorry. N is like total values, and S is like which doesn't have that player like which doesn't have that player I. So we are calculating this one, and this term, what this term is, including that I, like including that value I. For example, some terms will be there, A, B, C, D, like the A, B will be there. First, what is the main process is, like if you see like this A, B, C, you will be first taking like some BA, some AC, AB. You want to do for player, take for example player C you want to do. So you will just take the elements which doesn't contain C, you will take only them first. Which doesn't contain C, you will take them first. Then what you will be doing is, in this scenario, if C is added, what is the situation? That is the actual method of doing. But this is like very high, like it will take a lot of time to calculate for each and every player. So there is another better approach, like better easy way of calculation is there after this. You can see like this is explained. So see this example once. For player A, this is a situation like taxi fare ride is there. So for player A, it is like to reach station 6 it will take. For B, it will be taking 12, and C, like A, B, C combined, its marginal cost total is 42. So you can see the like values here. For A it is 6, B it is 12, C it is 42, like that it is there, values are there, and total combined cost is 42. Now we will be taking all the, like earlier one formula was there, no, we won't be using that formula. We will be taking this one by like proper permutation, we will be checking each of them, we will be checking. So what using Shapley value cost, how the 42 can be divided, like the total cost will be divided to each, like that we will be calculating next. So this is what this is what you will be doing. So what you will be doing is like this is not ABC. Don't confuse with ABC like that. This A, B, C is like player 1, player 2, player 3, like that it is. And this ABC is ordering, not the player ABC. It is like ordering. For example, in this case, show please. In this case, A is 6, B 12, C 42. So like this, next. It is there. So first A is doing, player A is doing first. So it is 6. And A is doing, then B is doing. So what AB combined sum is 12. So B will be filling that 112, and remaining ABC marginal cost is 42, it is coming C. And take this case here, BAC, what does it mean is like first B will be doing, so if B does, here you should fill here, like this is like 2, 1, 3, like that you should see, not like that. So B is 12, then this is like remaining cost will be filled. This is the example we saw here. Next. Yeah, even if player division looks fair, will the players actually stay in the grand coalition? That is also there. For example, I told that example before, political party example. Like if they bribe someone and they want to take the Z party from them, so will it really happen? No, right? So that situation is also there. So I will explain core part.
Before Sriman said whether the like division of values should be fair or not. Okay, so Shriman first explained that the like division of values are fair or not. But there is another one possibility that whether division of values are stable or not. Like stable in the sense any subset of, if we form a grand collision, any subset of that, they can form a collision on their own. And they all three will, like all the members will get better payoff compared to grand collision. So why will grand collision will be formed? Technically it should not be formed because with less number of people only you are getting better payoff. So core is a like it's a set of subsets, we can say, whether in which all the sets will have stability, like they have stability. Any smaller subset, not a full subset, like any proper subset, cannot form a better collision. Like either they cannot satisfy the criteria to get the payoff, or even if they get the payoff, they can't divide like better in a better way. So a payoff factor, like definition of core, like any set to be called core, the mathematical definition is that, so 100% efficiency, this is 100% efficiency, and for each value, like it is a subset, I belongs to S, xi summation of which should be greater than value of that whole subset. Like if they form collision on their own, it should be greater than or equal to at least. Like for grand collision or anything to be called core, subset should pay better than collision on their own. So here it is a parliament, like we can consider even Security Council meetings or a normal parliament game, where in a parliament 4 parties are there and they have this many number of votes, and majority is needed, 51 votes, to get pass the $100 million spending bill. Now in this Shapley value when we find, we get 24 are the total number of days, 4 factorial, 4 into 4 factorial is 24. But when we see like Shapley value to calculate for A, now A is 45. When A joins first, like 4 positions are there, and when A joins first, it will be 0 because no payoff is there. We are calculating marginal contribution. But A, if it joins second, then B should join first. If B joins first, then it will get payoff of 100. And CD can be like third and fourth position can be anything, so we can say into 2 factorial ways. That we can say. Or before A, even if COD joins and A joins second, in that way also we can count the number of ways. Like I'm just doing the intuition right here. But in that way we get total 12 number of ways out of 24 ways in which A can come and give some contribution. And contribution is 100 always because $100 million was going to spend. And from that Shapley values we get as 50. And similar for BCD, if we calculate Shapley values, we will get 16.67. Yeah, the Shapley, therefore, this is not stable because when A and B can form their collision on their own. Now Shapley value is generally for grand collision. Now A and B on their own they can form the majority and they can share all 100 million in any way, 75-25 or any split they want. Currently they are getting 50 and 16.67. So technically it's not good, like it's not stable, so they can form collision on their own. So now there are some properties of core. Is the core always non-empty? Non-empty in the sense like, so core is it empty or not? So here we can say that for okay, first I will explain why is core always unique or not. If you consider the rule 286 for majority, then we can say that ABC and ABD. In this case, only subsets which can form the majority for 80 votes are ABC and ABD. And in all other subsets, we can't form the majority for 80 number of votes. Now, in that, A and B are always needed to be there because 80 without A and B, both of them we cannot form. So A and B have veto power. So when A and B have veto power, we can force course to be stable for any collision to be stable. For non-veto players, we have to give 0-0. The intuitive way to understand this is like even if we consider all grand collision, since veto players can themselves form the collision, they don't need others. So themselves they can form the collision. Then other values should get 0 because if they themselves form the collision, they will get better payoff. So veto players have generally more power in core, and other players should get 0-0. So this is one of this possibility is a code, but this is not a Shapley value. Shapley value generally consider the marginal contribution and number of possible combination that marginal value is possible. So Shapley value basically says that it consider weights for marginal contribution as well, but number of combination that can occur. Like there may be some combination that if A comes second, then there will be lot of combinations. But if A comes third, then combinations will be less. But when A comes second, marginal contribution can be less. But A comes third, marginal contribution can be more. So accounting to all that Shapley value, averages all out, and then calculates the value like fair division, what it should be there. Fair division can be in many ways, but Shapley values whoever created Shapley theorem, they thought that averaging is better.
Shapley only doesn't take care of the fact what it's like all they will stay in that situation. The rest is the average finally and
So the simple game can be considered like a bipartite graph where we are dividing 0 and 1. So value like the payoff can be either 0 or 1. Even in parliament game what we saw, spending game can be 1 or spending can be done or spending cannot be done. So it can be divided. Now in that player I is called veto. It is a definition that except player I, if you don't involve player I, then value payoff will be 0 always. Doesn't matter whoever comes or whoever doesn't come. Now, the theorem states that the core is empty if there is no veto player, and if veto player exists, the core consists of efficient payoff vectors where every non-veto player gets 0. Here we saw that. And first theorem, the core is empty if there is no veto player. In 51 vote game, we saw that no veto player is not there, so that's why core is empty. So this was one example where there are three players, 1, 2, 3. And we need one is a veto player, and we need minimum two votes to get the value payoff. So 1, 2, 1, 3. Only those two combinations are possible. 1, 2, 1, 3, and 1, 2, 3 as well. So core here is 1, 0, 0 because one is a veto player, and others 2 and 3 are 0 payoff. And when we calculate Shapley value, this is a smaller example, so I can explain that. This is for player 1, player 2, player 3. Now when we consider player 1, when it joins first, it cannot get any payoff. But when it joins second, when it joins second, but first can be 2 or 3, anyone. So two possible ways are there. So 2 by 6. And this is for player 2. When we consider player 2, then first when player 2 joins first, it cannot get any payoff. When player 2 joins second, given that player 1 joins first, then it can get payoff. So it is 1 by 6. Similarly, 1 by 6 for player 3 as well. So when we calculate 2 by 3, 1 by 6 and 1 by 6 we will. This was one another topic for mixed games. In this we also it was a set theorem, right? Here we minus the intersection value, intersection of those what payoff they give. In Shapley we consider that sets are independent, they are not their intersection is 0 in Shapley axioms, but here we are not considering that. That game is called convex. And in this small talk we discuss profit sharing, voting power, cost sharing,